Okay, so you have a graph like this one, and what I have here is just what I showed you before. Not much, it just generates a random graph, and I'm showing it to you. And now let's say you want to solve this problem. Now you want to build distributed algorithm that can find graph coloring, if there is one. How do you do it? Well, you want to do it distributed, so you want to have each node be an agent, right? So sort of the first thing you might think of is, well, if each one of these guys is an agent, so just have them look around and find a color that works, given his neighbor's colors, and set himself to that color. So let's do that. Right? So the obvious thing, I'm gonna add a go button for that. Go, and then come down here, and we're gonna have some node functions down here, and to change color, and I'm going to do a for each in the colors. Remember, the colors variable was the colors of that are possible, our domain. If the color does not violate any of the is colors in my neighbors, they're not. If not any link neighbors with color um, equal to this color. So if there are not any has a question mark. If there aren't any neighbors with that color, then I'm going to set my color to that. And that's it. I'm done. Otherwise, I stay at the same color. Then to go, tick ask nodes to change color. Sounds good. And so I'm going to tick there. That means I need to reset ticks there. Set up, lay it out, go. Okay, so they change colors. We'll want to know how well we're doing. So let's set up a little plot here that we can see how well we're doing. So plot of constraint violations. So I want to show the number of constraint violations. So that's going to be the count of the links with what? With n1, no, color of n1 equal to color of n2, 2, right? So each link has two ends, n1 and n2, which are nodes, and if their colors are the same, then that's a constraint violation, so we count it. Okay, make this a little bit bigger. Set it up, lay it out, and go 15. It drops down, and then we get stuck around what, 5, 6. So yeah, it gets better. Starts at 20, drops down. So it's a start, right? So the simplest algorithm does something, and it improves the solution, but not terribly so. So what's the problem? I mean, how can we make this better? Well, one thing you notice here is that I am, I'm only looking for any neighbors, any color that has, where I have no neighbor with that color. So, but the situation could be that there is no such thing, right? So I'm gonna go over here, erase that. Um, so it could be that I am, the blue guy here, And there's another blue guy over here, right? And there's another red guy over here. And there's another green guy over here. So, or maybe there are something like, well, this. So, so this guy here in the middle, he can't set himself to any color, right? We only have red, blue, and green, so there's nothing that's going to work for him. But he's blue, and there's all these other blues around. But given this, he's not going to change because red doesn't work. In reality, though, he probably should be red, right? So he should be red, and because that's sort of the best color. So we call that the min conflict heuristic. Heuristic basically means go for the color that has the smallest number of conflicts, which in this case would be red. So that might be an improvement. Another improvement might be like in this case, this is ordered, right? So it's always in the same ordered. So if there's a tie, so order means or implies that ties always goes to the same guy. Always goes to the same guy or node in this case, right? And that is bad. So we don't want order stuff. So we want to handle ties like when if there's two reds, for example. If there's two reds, then this guy should choose between red and green randomly rather than always going to red when there's a tie between red and green. So those are two simple things we can do. Let's do them. So what we're going to need to do then is find out for each color how much it costs, right? So each possible color has like a cost, which is basically the number of constraint violations. So let the color costs be what? So it's going to be like a map over the possible colors of something. Basically, I'm going to need to calculate the cost of color like that. And actually, what I actually want is I want this to be an associate list and an ASOC list of pairs color cost. So it's going to be color cost for this other color, what is the cost, and so forth. So it's not going to be like this. It's going to be like a list, a list of the color and then the cost of that color, which I haven't implemented yet. So to report, what is the cost of the color? What could that be? Well, that's going to be the sum of the total number of neighbors report, the count of the link neighbors with color equals the color, right? So that's good. So those are my color costs. So the cost of each color. Now I'm gonna need then my main cost, the minimum cost. Let the minimum of those costs is gonna be the minimum of this and this. So I'm gonna need these values here. So I'm gonna add some associate helper functions. Basically, these are just some helper functions to help me deal with lists like this, which is basically a table, right? It's a key value pairs. So I'm gonna need something like to report, like to get all the values is what I need right now. I'm gonna call this an A list. right? Because and the idea is an associate list, an A list. We're going to assume is list of key value pairs like such. Like that. So I need to get all values. So this is a map, right? Map of over the A list of, oh, it's just the item one. And we're going to report that guy. Return it. Okay, so that sounds good. Get all values. Let min costs. The min of get all values of the color costs, right? So that is the minimum cost, color costs. And now I'm gonna need, so once I find the minimum, I'm going to need the values, so the key, all the keys that have that value. So another helpful function. To report get all keys with for value value. So a list value. And that is going to be, again, well, it's going to be a filter first. First, we're going to need to filter out a list so that it returns just the first ones, right? So we could say one the chosen has to be equal to value. So this is going to be a list of pairs, and I need all keys. So board map is just like the other one. First question mark a list. So get all keys is going to return get all keys, and get all keys of that is what we need here, right? I think so. So get all keys for a particular value. So this is returns list of all the keys in a list that have value. So get all keys, right? So we go down here. So where were we? Min cost. That's the min cost. Now let best colors is going to be the get all keys for value. So first is the A list, which is the color costs, and then the min costs. So best colors is going to be the set of all colors that have that min cost. It should be min cost because it's just a number. The min cost. And then I just need to set my color to one of best colors. So just choose randomly from those. They're all equally good. And I can get rid of these old stuff. So yeah, this might or might not change the color, but okay. So let's see if this works. Set it up, lay it out. Nope. There we go. Go. Dropped a little more. Hey, got down to 0. Let me put in a monitor here. Well, let me cut and paste this. I don't have to type it again. So I just want to add a monitor here so I know if it's actually 0. No decimal places. Need that. Didn't work. Yeah, no plot there. Okay, set it up, laid out. Go, 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 go. One. Set it up, laid out. Nope. Go, 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 go. So, you can just from doing a couple of examples, it already seems better. You know, still doesn't always converge. I guess pretty low. Go, 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 go. Down to 3, down to 2, down to 1. And of course, this is not scientific. You have to do it 1,000 times and then it's scientific. Um, but there you go. It's pretty good. Now we can do better. Hopefully, I think we can do better. So again, we're only changing color to the one with min conflict, and that works pretty well. But if you run this a lot and you do with the data, you'll notice that you still get stuck in local optima basically because one of these guys might he they're still only looking at their neighbors, right? So they're only thinking, each node only thinks of itself. He doesn't think beyond that. And so sometimes they get stuck in a local optima where these are fixed in their colors, and really the only way to get out of it is for two of them to change at the same time, or more. So we can improve this a little bit, and the basic idea is as follows. Let me see. I think you want to erase this, and I think maybe if I go over here, it'll be better, easier to see. So what here's the situation. So we have a graph here, some nodes. So two things we're gonna do next is first thing is we're gonna think about the gain. We call it gain. So or how much there is. So right now this guy just looks, he's like, I'm blue, my neighbors are either red or green, and I just change, so like there's a minimum to the best possible color, right? So we can think of it instead as the gain, right? So we can say how much you have to gain from changing to red or changing to green. In this case, negative, right? You lose. So let me add some more blue. But if you had something like this, now we got 3 blues, so you have like your gain would be 1 if you change to green. So you think of that, and then the next idea is we can take each. Right now we're counting each edge as one. They're all the same, but you can. The idea would be to dynamically so initially have them all start at 1, but then dynamically raise them. So if we found out that we're blue and that didn't work out, I don't want to keep flipping back to blue again next time. So I might change to red and then go back to blue. So the idea is that we can then, after we change away from blue, we can look at these 3 links and say, I'm going to raise their weight to 2. So then the cost uses these weights into account, right? So the idea is to label edges with a weight and use it in the cost function. Right. So that's one thing, first thing we're going to do. And the other thing we're going to do is we're going to look at quasi-local optimum. Using this gain over here. right? So, right, you say right now we're just looking at what's best for me. But let's say this, which is great, he's utility maximizing, he's doing what's good for him. But let's say he, instead of doing that, he asks his neighbors, hey, how much, what's your maximum possible gain? And yours, and yours, and yours, and yours. And then this guy, if he sees, this guy over here, his maximum gain is say 4, and mine is 2, by say changing to green or something. I'm gonna let him do, I'm not gonna do anything. I'm just gonna not do anything, and which means he is, maybe, depending, he might have another neighbor with a higher gain, but assuming he doesn't, then he's gonna change his color. And why would we do that? Well, that helps us get out of the local optima. Right? The local optima, I only look at my gain and like, oh, I got a positive gain, I'm changing. The quasi-local, I'm going to look at my neighbors also, and I'm going to say, well, you guys, have better possibility. By changing your color, you can reduce the total cost, and really, isn't that what we all want, to reduce the global cost? So I'm gonna let you do it, and then maybe next time after you do that, obviously, or not obviously, but maybe your cost will be lower, and then maybe after I get to change after that. But um, so we let the ones that can have the highest gain, not just me, change. And so that prevents us from getting stuck in little local optimas. At least that's the idea, and it turns out to work out pretty well. Okay, so let's do that. So first, I'm gonna label the edges, and let's go back to that logo. So labeling the links or the edges is fairly easy. So I'm just gonna say links own a weight, and down here I'm gonna ask the links to set the weight to 1 initially, and then set the label to the weight, and set the label color to black so we can see it. So there we go. Now we should be able to see those ones there. Of course, not using them yet, but so we can use them in the calculating the cost of a color, right? So right now I'm just doing this. I'm just counting how many neighbors have the same color. I actually need to not do that. I need to count the number of links, and then well, use their weight. So try to figure out how many links have are conflict links. So we don't need that anymore. So I'm going to report the sum of what? It's going to be the weight of, well, I'm going to call it a conflict links. And of course, I haven't defined that. And they're actually going to be the conflict links for the color, right? So the set of links that are in conflict if I was this color. So I'm going to need that. And so this is going to return a set of links that would be in conflict if I was the color. So my links are my links. So my links with what? So I want the links that point me to somebody who has the same color. Of course, one of the other ends points to me. So what we need to do is with n1, if n1 is not equal to myself, that means that n1 is the other guy. And color of n1 is the color. Or and 2 is not myself, and color of N2 is the color. And yeah, we gotta report all this. So report my links with N1 is not equal to myself, then color of N1 is the color, or N2 is not equal to myself, and color of N2 is the color. So those are the conflict links. And then the color is just going to be the sum of the weight of those conflict links. So that looks good, right? So we're just changing, and then this should fit in because I have cost of color here. That should fit in just fine right there. Now, for the gain, I'm going to need to calculate the gain for each one. So I need a gain calculation function, best. And so this is gonna report my best gain and color, in like best gain, best color, like in a list like that. Sounds good. And so most of this is gonna be this. So I'm gonna move all that down here and then massage it. Not gonna be setting color here though. That's gonna be over here. So I calculate the best color. So I got my best color, and its cost. I need, so for the gain, I need to know, yeah. So my gain is is the difference between my current cost and the cost if I change color. So my current cost is going to be what? Well, they're over here, right? So I already calculated it. So I just need to get value. Did I implement that already? No. So I need a little helpful function to report. Get value key. So given a key, I want to report the value of it. This is, assuming, of course, there's only one. Right. So how does that work? Need a for each in a list, yeah, a list. So for each value in the a list, if first question mark equals the key, then report item 1 of the question mark, right? Otherwise, keep going, and then at the end, error, no such key. So that should never happen. If it does, the whole thing would crash. So that's my get value, and yeah, it's just, this is like a get in a hash table, right? Okay, so where were we? The current cost is going to be the get value from the color costs, and then the color, which is color, and that's the key. The key is my color cost is a map of key value, so that's my current cost. My main cost is my main cost, so then my gain is if my min cost minus my current cost, right? Because if the min cost is bigger, then it's positive. Nope. The other way around, I always get that. So the current cost, if the current cost is bigger, the current cost is bigger than the min cost, then it's going to be positive gain, right? If the min cost is bigger, which really cannot be, but this the gain can be at best 0. So, but yeah. So we just need to then report the list of what? The color. And the color, I have best colors, so you know it could be any one of them because they're all, it's a tie, right? So one of best colors, and then the gain is the gain, right? Best gain, best color. Okay, I'm doing it wrong. First is the gain, then the color. Right? So best gain, best color. So to change color, I'm gonna let gain dash color be best gain color, and you know what we were doing before, we would just set color to the second one, right? We would just set color to item 1 of gain color. So that compiles, right? But we're still not doing what we said we're gonna do. But we got these gains, right? So the idea is that we're not gonna always change color. We're only gonna change color if my gain. So I'm gonna let my gain be the first in gain color, right? So and let the others gain, everybody else's gains is gonna be okay. So it's best gain color of my linked neighbors. That is going to give me all their gain color pairs, and I don't need the colors, I just need the gains. And so I already have the get all values function. Get all actually get all keys, right? So I want and the gain of all my neighbors. So this is going to be the gains of all my neighbors. Just going to put some parentheses here to make it more obvious. And then I want the maximum. Max neighbor gain. So, okay, so only if my gain is greater than or equal to max neighbor gain do I then actually go ahead and change my color. So that will be when I change my colors. That's what I said. That's what the quasi-local minimum tells us. We're only going to change our color when our gain is greater than or equal to our neighbors, or you know, the best from our neighbors. And awesome. And then when I do that, I also want to increase the weights of the links that were in conflict, right? So luckily we already defined this conflict link. So conflict links of my current color, those are, you know, the conflict links. So I'm gonna ask those guys to set their weight to be weight plus 1, and then set the label to be the weight so we can see it. Okay, so that should do that. Let's check this out. I set it up, lay it out, go. You see where some increases to 2, goes down, 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 goes up a little bit, down, up, down, up, and it keeps fluctuating a little bit. But Yeah, we're at 1, 2. It's pretty low. There, 0. So 0. So, we just did a couple ones and we got it down to 0. It works pretty well. So this is distributed breakout we just implemented here. At least, I claim it is. It's I claim, the basic idea of distributed breakout is implemented here, I believe. We can look at the actual algorithm. If you see it right here, is distributed breakout in chapter 2. You can see the main ideas were here, right? Where is it? You have to send improve here. Only if my improvement is better than all of my neighbors, then I change my color. And if my cost, if I am in a, if my cost is bigger than 0, and and for all my neighbors, they're stuck, then increase the weight of constraint violation. So yeah, this is not exactly, we didn't get this exactly right. So let's do that. So if my cost is bigger than 0, and for all my neighbors have negative gain, basically. That's what this is saying here. Then we increase the constraints. So I got that wrong. So it's not here. So my gain is positive. Yeah. So that's fine, but it's just not. This needs to move. Down here, and the constraint is if my gain is bigger than 0 and everybody else's gain is less than or equal to 0. And the max, so that would mean max neighbor gain, the maximum has to be less than or equal to 0, right? That's when I do this. Sorry about that. So hopefully I got it right this time. Okay, so set it up, layout, go, 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 go. So you see, increase a couple times. 1. Will we get to 0? Now, it could be that this has no solution, by the way. So you can do better testing where you generate graphs that have a solution. It's pretty easy to do that, right? And then run the algorithm and find it. So 0, that's good. 2, I think we're stuck in 2. But so okay, so this is distributed breakout. See, it doesn't work if the graph is not connected. Okay, so now I think we got it right. So you see, it's basically the same idea. There's a couple things that they do here, like they wait for improving from the other guys. We don't do that because this implementation, as you might notice, is not really distributed, right? We're kind of cheating that I am able to access the best, everybody else's best gain function, best gain color, which means I can get their color, the current color, etc., without doing any messaging. But I think the only difference would be in the timing. The main logic of the algorithm remains the same. So anyway, it's a lot of fun to play with. So you can get the code and copy it and start playing with it and see if you can improve on it. One of the things is, the final thing is, I've written several papers on distributed breakout, and variations on it, testing it on the graph coloring problem, for example, and the results are really, really, really good. Like 99.999% of the time, it finds a solution, when there is one. Uh, and it does so, as you can see, really, really fast, right? So it drops off really quickly, and then it's only at the last little bit where it has trouble. So for random grabs or randomly generated graphs in graph coloring, it does really well. Really well. I don't know about other domains. I don't know if people have looked at that, um, but it's a simple technique that seems to work rather nicely.